This huge map contains almost 10 million underlying tiny squares and 160,000 larger hexes with dynamic weather. Tens of thousands of animated units move across an expansive network of roads, bridges, and rivers. Millions of trees, rocks, foliage, and other objects cover the terrain. A save game for such a huge, densely populated world can easily approach 1 GB in size. How do we write all of that onto disk quickly enough that the player barely notices? As is so often the case, the secret lies in memory management. As we've seen in previous videos, huge game worlds come with many challenges, most of them centered around making sure everything happens fast enough to preserve the flow of the game. This becomes even more important when players can edit the world, including its terrain, in real time. Giving players this much freedom requires storing an enormous amount of information, even if we are frugal with the data types, for example using half-precision values. Of course, players should be able to save the game and continue the journey later, and autosave is also an important quality of life feature. As with everything else, we don't want saving to interrupt the flow of play. Luckily, the way we set up our data structures in large native memory containers to allow for burst-compiled parallel jobs is also very beneficial for writing to disk. Take the tens of thousands of units as an example. If we store each unit as its own object somewhere in memory, we'd have to chase after thousands of pointers to tiny scattered blocks of memory. So instead, we store all their positions, health values, animations, and other data in a handful of large native lists. Each list occupies one big contiguous block of memory, and modern storage devices are extremely good at writing large sequential blocks of data. To actually write the data to disk, we define a simple binary writer interface, which requires a write bytes method. Every save operation boils down to this one function. It receives nothing more than a pointer to the start of some memory and the number of bytes to write. Once you have that, writing almost anything becomes trivial. Single values, native arrays, and native lists all reduce to the same operation. Point at some memory and tell the writer how many bytes to copy. So, we create static methods for the interface to save any data type we need, and can even define a generic method that handles any unmanaged type. We also define methods for writing native arrays and native lists by supplying read-only pointers to their data and specifying the number of bytes to write. Note that we cater for compressing the data before writing it. This reduces disk space required by about 60% in this example, but greatly increases save time to around 29 seconds if we stay on a single thread. For autosaves, we would generally ignore compression to speed things up, but we could give the player the option to compress manual saves, trading speed for disk space. The implementation of write bytes itself is surprisingly simple. We create a file stream with the supplied file name and allocate a temporary byte buffer. Chunks of memory are now copied from the source pointer into that buffer and written to disk until everything has been written. It's as simple as that. The secret lies in already working with large blocks of contiguous memory and pointers to those blocks. Of course, there will always be some data that isn't stored in large native memory containers, but if everything has been designed for burst-compiled jobs, those would be minimal and should not significantly impact the time it takes to save. Loading follows exactly the same principle. As long as the data is read back in the same order it was written, the native arrays and native lists can simply be recreated with their saved capacities and lengths before the contents are copied back into the native memory. And that's how we save 1 GB of game state data in less than half a second with barely an inconvenience to the player. Please like if you enjoyed the video, leave a comment, subscribe to this channel, wishlist and follow Minor Deity on Steam, or join the Discord server to stay up to date. All the links are down below. Also, feel free to ask specific questions you may have. Thanks for your time and support.